on this. Okay, good morning, everyone. This is Chemistry 2341, Organic Chemistry 1. We're going to continue on with radicals today, and I left you with a bit of a cliffhanger on Monday as to why these reactions did different things with different halogens. But before I do that, let me go ahead and give you some administration stuff. Again, all we have module 10 will be due Monday at midnight, November 16th. Which is our week. I'm sorry, that's November 23rd, the week of Thanksgiving. Okay. And I want everybody to have a safe Thanksgiving break. And so try to distance as much as possible and come back to us healthy so that we can finish out the year strong. Okay, we're going to continue on with module 10 radicals today. I should finish it today and I should start module 11 on Friday. And that gives us Friday, Monday, and Wednesday of next week to complete our last module. When we come back from the break, we're going to do a group activity called reaction tables. And so this is basically going to help you kind of organize everything that we've done so far in these 11 modules to help us prepare for the final. The final will be cumulative. And so everything from chapter 1 through chapter 11 will be there. And we need to kind of have a way to, number one, strategize our studying. The good thing is we'll have an exam on December 2nd, Wednesday, December 2nd. And so that we should have modules 8, 9, 10, and 11 studied for already, because those are what's going to appear on the exam number 3. But then you got to remember that we also have chapters 1 through 7 that we are also going to be coming on the final. And so we need to go ahead and find a way to remember all those things and organize all those things in a way we can use them. So that's what will be happening over the next couple of weeks. So without further ado, let's go ahead and share my screen and move on with radical chemistry. So I'm going to move my thing up here. If anybody's wants to wave. There we go. All right. So here we are with our reactions we saw last time. And I said we have a collection of these radical reactions. They're different than our other reactions because, number one, it involves a single electron coming in and using that single electron to do chemistry. Every reaction up to now, we've used a pair of electrons to create that new sigma bond. Here we're using individual electrons. And because of those individual electrons, we're going through a radical intermediate, which is an unhybridized p orbital that has a single electron in it. And so it's kind of, the same as a carbocation, but that is trigonoplanar and has no electrons on it. And it's kind of halfway in between that and a carbanion, which is in an unhybridized p orbital with 2 electrons in it. And that forces things out. And so we're right there in the middle. And so they tend to have the same stability trend as those of carbocations. Okay, so that gave us to this selectivity and halogenation reactions. And we found out that using different halogens give different product ratios. And so we have to define why we get these different product ratios. And I'll give you a hint. It has to do with 2 things. It has to do with a little bit with statistics and a little bit with thermodynamics. So between the 2 of those, comparing and contrasting statistics and thermodynamics, we should be able to predict these halogenation reactions in these hydrocarbons. Okay, so to review what we saw last time, we have our fluorine right here gives a different product ratio than chlorination. So our fluorine is mostly the primary halide and a little bit of the secondary halide. Chlorine right here is about 50-50. Okay, so there's going to be something about the thermodynamics of those and the statistics of those that give rise to those 2 numbers. When we get to bromination, we see high selectivity. We get the bromination at that secondary site selectively because of thermodynamics. And iodine doesn't work at all. And it doesn't work at all because of thermodynamics. All right, so now we also put here, down here, that statistically, we have 25% should go at this site and 75% should go at that site. Okay, what that means is we have three hydrogens here, and 2 hydrogens here, which gives us a total of 8 hydrogens, which means 25% of those are the secondary hydrogens, and 75% of those are the primary hydrogens. So that's where the statistical part of it comes in, how many different hydrogens we have on each of those 2 different sites. All right, now let's dive into the thermodynamics and figure out why. Okay. So if we use that same thing we did with the bond energy breaking and the making, what we can see is that if we subtract all the bonds broken from all the bonds formed, we should get the net result of that reaction. Okay, so using those bond dissociation energies, we can kind of add those up and figure out whether the reaction is endothermic or exothermic. Okay, so if we look at the first step in this, we have the breaking of this primary hydrogen for that primary carbon. And if we look at that big table, we'll find that and see it takes 422 kilojoules per mole to do that. Okay, and now we're going to lump in all of the halogens so we can look at them in series. Okay, just breaking these halogen bonds, it's not as much, and they're all similar, with the chlorine being the highest energy to take to break that bond. Okay, so we have to take that into account. Now, those are the bonds being broken. Okay, so now let's look at the bonds being formed. So this is the product side of the reaction here. One of the things we're going to form is the H halogen, the acid of the halogen radical. And we can see the formation energies are quite high for fluorine and chlorine, and then they kind of drop off around iodine. Okay, but then also the energies that we get from making these bonds, fluorine carbon bond is a very strong bond and has the highest energy available to it, and gives us, and it kind of goes down after that as the atoms get bigger and bigger, the bond gets longer and longer, and so it has less and less energy. Okay, so what's the net result of this? Well, the net result of this is this table here. And what we see is that if we subtract the reactants from the products, we end up with this number here. And if we subtract the reactants of this reaction with the reactants, the products of this reaction, we get this here. And if we add those together, this is the net heat change, enthalpy change in the reaction. Notice for fluorine, we have a very high enthalpy. We give off massive amounts of heat. It's really, really exothermic, 463 kcals per mole, kilojoules per mole. Okay, and when we go to chlorine, it's still exothermic right here, but not as exothermic. So we might start to see it saying, oh, okay, it's less hot. It's going to react a little slower maybe. Now, once we get to bromine, it's barely exothermic at all. So there might be something about that reaction moving slowly, and that slowness of the reaction allows us to put things in a specific location. And then this last one we have here is the iodine. Remember, iodine didn't work at all in that previous table. And the reason it doesn't is because the net overall of this reaction is it's endothermic. There's no driving force for the iodine to make this halogen. That means that the halogen radical is more stable than trying to form that carbon iodine bond. So the reaction does not work at all. Okay, so let's go ahead and see that kind of ties together exactly with the table we saw here before. Okay, so if we look at that, instead of looking at it as the primary, let's look at it as the secondary. There's a slightly different energy to abstract that hydrogen radical from a secondary carbon. In fact, it's a little bit lower. All the other values here and here are the same, but the values for making these bonds are a little higher. Notice that the secondary halide bond here has a little higher energy in it until we get to the bromine and the iodine. Okay, but the net result of that reaction for all of these forming the secondary is we have very exothermic, a little exothermic, a little exothermic, and endothermic. So the iodine doesn't work at all on the secondary either. Okay, so notice that it's more exothermic on the bromine, a little more exothermic on the chlorine, and a little more exothermic on the fluorine. Okay, so in theory, the secondary is favored thermodynamically because it gives the more stable thermodynamic product. So that means we must also have a kinetic component associated with it. All right, so let's kind of look at that and as a function of the initiation of the reaction, that forming that transition state, and then cascading down into products. Okay, so if we immediately just compare the fluorine and the iodine from that previous table here, we saw that the fluorine carbon bond and the fluorine hydrogen bond created are very strong bonds, and that reaction is very exothermic. Then we also saw that iodine didn't work at all, and it had a positive heat of enthalpy, change in enthalpy there. That positive heat of enthalpy says that it is an endothermic process, and therefore that means the iodine radical is more stable than trying to abstract a hydrogen from that alkane, meaning the reaction does not go. Okay, so that's the two extremes of that end, the really, really exothermic and the endothermic, and that explains why they react. Okay, let's talk about the chlorine and bromine a little bit. So when we look at the abstraction of the primary or secondary hydrogens, if we do it with the fluorine or the chlorine radical, it's both exothermic. The primary abstraction of that primary hydrogen is slightly more exothermic in fluorination and chlorination reactions. Therefore, it tends to have them happen more easily, okay? The difference between the bond association and attribution of fluorine and chlorine reactions is not, the large difference there is because it makes it the chlorine far less exothermic than both of the other propagation steps, the abstraction steps, the radical formation steps. Now, bromine radicals are more stable and they form weaker bonds. So if they're more stable and form weaker bonds, then it's going to wait around a little while and be picky about where it goes. It's going to be selective about where it goes. What we also learned was in that table is the abstraction of hydrogen from bromine radical is endothermic. So part of that reaction is actually that endothermic part of that reaction is slowing the reaction down. And then the actual abstraction at that secondary hydrogen is slightly exothermic. So this is at a primary hydrogen here is endothermic. The secondary is exothermic, meaning that when we use bromine, it would prefer to abstract that secondary hydrogen because it's the more exothermic of the two reactions. Okay, so now that's just comparing the primary hydrogens versus the secondary hydrogen. Okay, now, do you remember the Hammond postulate, the one that said, if the transition state is more like the starting materials, then the reaction is exothermic. If the transition state is more like the products, that means the reaction is endothermic. Okay, what that means is the bond that is forming is less than half formed in the transition state. So if you can think about it, the forming bond, the thing coming in, is further away, is less than half of a bond formed, and the leaving group has more than half of a bond formed. Okay, so that makes it wait a second, yeah, more than half formed. So that makes it looks more like the transition state. If the bond breaking is less than half of the transition state, then the transition state, then it is more like an exothermic reaction, more like starting materials. So in an endothermic reaction, the leaving group's already starting to leave, okay? And the bond being formed is more than halfway, and the bond being broken is more than halfway. So it's looking more like the products because the leaving group is more, has left more, gotten further away from the nucleus. So it looks more like the products. So that's the difference between an endothermic, is the leaving group is less than halfway gone. In the endothermic process, the leaving group is more than halfway gone. Look at it that way. Okay, so what does that mean? In these radical reactions, that changes the depth of the uh, activation energy required to do that early transition state. Okay, so in fluorine, there's a negligible activation barrier for forming the primary or the secondary because there's not very much difference in that. And what that means is that because it's an exothermic reaction, that the fluorine atom in the transition A is far from the hydrogen is abstracting. And the hydrogen is very close to the carbon as it's abstracting, leading it to have this small transition state, and it looks more like the starting material. Now, once it does abstract that, it cascades down into forming our two products. And of course, our secondary radical is more thermodynamically stable because it's stabilized as a secondary, not a primary. And if it was a tertiary, that'd even be more thermodynamically stable. So, but remember, we're getting here because there's very little difference in energy at the transition state here, meaning that either pathway can go during the early transition state, and therefore we get both of these products from our system. Just that intermediate step. Okay. In the case of chlorination, there's a slightly bigger difference in taking the primary versus taking the secondary. And that slight difference in that energy of transition state here leads to it being less selective in saying that it's going to be a primary or a secondary, because our transition state is at that intermediate level and we have more of the secondary forming than the primary forming. Okay. And therefore it does give us more of a starting material like character, but we form this in approximately equal amounts. Okay, so what does that mean? If we do that with bromine here, because the abstraction at the primary site is endothermic, it has a much higher transition state here. Okay, that means if it has a much higher transition state, you have to hit a lot of energy into that system, and more of these are going to react before you even have enough energy to get to here. Therefore, because that abstraction of that primary hydrogen is endothermic, we get almost exclusive abstraction of the secondary hydrogen, leading it to the major product. Okay, so notice the big difference here in these is the fluorine, very small difference in transition state, chlorine, a little bit bigger difference in transition state, bromine, a huge difference in transition state. Okay, so that's why we end up with this selectivity principle. If you have a very highly reactive system, think very exothermic, you have very low selectivity because the reaction goes quickly and it can go through multiple pathways. For example, that there's a barrier between those two fluorine initiation, the abstraction of the primary and secondary are very small, and it's exothermic. So just the abstraction adds heat to the system. So just that abstraction adds heat to the system. Therefore, it's going to do either. It's going to do both. It's going to do primary and secondary with very little selectivity. The opposite is true for bromine. Bromine, one of them is endothermic, one of them is exothermic. Therefore, that gives us a much lower reactivity. When we have much lower reactivity, we have higher selectivity. So because the abstraction of this primary hydrogen was endothermic and the secondary one was exothermic slightly, we get the major product because of that more easily abstracted hydrogen, and we get selectivity in our bromination. So think about the fluorine being incredibly reactive and therefore very low selectivity. Bromine is very low reactivity and has very high selectivity. So chlorine must be somewhere in between. And there's got to be a reason it gives a different product ratio. Okay, so if we think about fluorine, and it has very little selectivity for where very little difference in energy between a primary and a secondary hydrogen abstraction, then that means we now have to go to statistics. Okay, I told you before we have 3 of these primaries on this side, 3 of these primaries on this side, and 2 secondary hydrogens available to us. That's giving us a total of 8 hydrogens. Okay, so any one of those 8 hydrogens can be a target for that fluorine radical abstraction. Okay, now statistically, because there are 6 of these primary hydrogens and 8 total hydrogens, that means 75% of the time, just statistically, that fluorine radical is going to abstract one of those. Okay, so it gives us a product ratio that should be about 75% primary and 25% secondary. And if we did the statistics on the secondary one here, we only have 2 of these out of the 8. 2 divided by 8 is 1/4 or 25%. So we should get about 25% of the secondary abstraction. Okay, so that means fluorine is so reactive and the energy barrier difference between the primary and the secondary hydrogen abstraction is so small, we're down to statistics. It's just how many hydrogens you have. Okay, and the stability of the intermediate doesn't matter. The reaction is self-heating, it's propagating itself, and we're down to just statistics giving us our selectivity. Okay, so how does that apply to chlorine? Okay, well, it turns out each of the halogens, because of that activation energy, has a certain relative selectivity for halogenation. So for fluorine right here, if we take everything as primary is 1, so we're just being able to do a relative selectivity there, secondary is 1.2. So that means for every 10 primary radicals you create 12 secondaries. So it's very little selectivity there, and tertiary is about 14. So those are all about the same order of magnitude. Okay, chlorination is a little bit different because it has a different heat of abstraction. We start with chlorine at 1, and then it's 4 times more selective to a secondary and 5 times more selective to a tertiary. Okay, so it's not as exothermic reaction, so it does have some selectivity in which one it's going to take out, and it's going to selectively take out the more stable to leave the more stable radical on your substrate. So tertiary radicals are more stable than secondary, more stable than primary. So that's why we have a 4 times more relative rate in the secondary and 5 times on the tertiary for the chlorine. Now bromine, because that is the primary is actually an endothermic reaction, we see a much bigger difference here. So in the bromine, we see that if we take that one, that endothermic one is 1, it's 82 times faster to take off that secondary and 1,600 times faster to take off that tertiary. Okay, so what does that mean? Okay, so this is the selectivity ratios relative to the different halogens. Now let's apply that selectivity and the number of possible bonds formed and see what our product ratios might be. So if we go down here and do 2 examples right here. So in this particular case, right here with this substrate, we have 1, 2, 3 primary carbons and 1 secondary carbon. We have a total of 9 primary hydrogens, and 1 tertiary halogen. Okay, so the selectivity difference between a primary and a tertiary for chlorine is 1 to 5. Okay, but we have 9 times more primaries. Okay, so we have to take that into account. So when we take that into account, we have a relative reactivity ratio of 1, but we have 9 hydrogens available to us, which should give us a total of 1 times 9 is 9, plus the other reaction available to us. And tertiary is 5 times faster, but we only have 1 hydrogen there. So that means it's the 5.1 times faster times the 1 hydrogen. So the total number here is going to be 14.1. So we have 14.1 types of reactions that can happen at any time, and 9 of them happen on the primary, and 5.1 of them happen on the secondary, meaning our product ratio is going to be 64:36. Okay, so we're taking into account the reactivity ratio and taking into account the statistics of the number of sites available. Okay, so that's what we're doing here in that. Okay, let's apply that same rule to that same compound for bromine. Okay, we have that primary, which is our 1, our tertiary, which is 1600. We have 9 at that relative reaction ratio of 1. We have 1 at the relative reaction ratio of 1600, giving us a total number of 1609 for possible reactions available to us. And 9 of that 1609 is only 0.6%. So even though there are 9 of those hydrogens there, the reactivity ratio is making the tertiary product the primary product. In fact, you might not even be able to analyze the material and see that other product in there, but it is. Okay, so this is the value of knowing the reactivity ratio and number of available abstractable hydrogens to predict your product ratios. Okay, so what does that mean? Okay, so in our previous reaction, we had our primary and our secondary for our fluorine. The fact that there's very little selectivity difference means that it's only driven by the statistics. Chlorine, we start to see statistics playing a role, and that's why we get, it's 4 times faster for a secondary primary. So that's why the reactivity ratios become equal, because we have a 6 hydrogens to 2 hydrogens. And so that's starting to get them close to 50-50. But in bromine, it's a 1 to 82, and we get more of the product as we got 91% of it or 92% of it as the primary, secondary, and only 8% as the primary. Okay, do we see how we can use the joining of that reactivity ratio and the statistics to give us that the product ratio of our reaction? Okay. So, and do we see how that difference in activation energy is also driving the selectivity? So this rule about the more reactive, the less selective is very important. The lower the reactivity, the more time it has to sit around, wait for just the right amount of energy, and be highly selective. Okay, so with no questions there, let's go ahead and look at some stereochemistry associated with halogens. Now, what we're going to see here, okay, cool. Okay, so what we're going to see here in halogenation is because we are going through an unhybridized p orbital, just like in a carbocation, we should see some similarities to the stereochemistry associated. However, there is one big difference in the radicals that we don't have in the carbocations. Okay, so as we would expect, we change hybridization on the other bonds there, and we get this unhybridized p orbital. So that's above and below the plane, and the incoming radical to form our new sigma bond can come above or below the plane of where that is, meaning that we have a mixture of R and S, a 50-50 mixture of R and S in our secondary position, in our primary position, we don't have chirality because we have 2 hydrogens left on there. So in the case of our secondary radical here, we can get a 50-50 mixture of R and S. Okay, do we see why there's no selectivity, right? It's just like a carbocation because our nucleophile is coming in from the top or the bottom in the carbocation. In this case, our radical can form our new sigma bond at the top or the bottom. So there's mixing of stereochemistry. Okay, however, what we also see is that carbocations do not rearrange. I'm sorry, radicals do not rearrange, carbocations do. So this is actually very important for us because what we can see here is we can put bromine kind of where we want it in this reaction where we can't do it with a carbocation. For example, let's say we have, let's look at this compound here. 1, 2, 3, 4 sites. Those are all primary sites. So that means the relative reactivity ratio is 1 to 82. So that means that we're going to get most of our reaction occurring at this site here. And of course, the first step in that is to abstract a hydrogen, leaving a radical on this secondary carbon. Okay. Radicals do not rearrange. Therefore, our new sigma bond with our bromine is going to give us the secondary bromide and then a radical, and it continues on and on. We're going to get a little bit of bromination here, 8% total right here, but most of our bromination that we're going to get is right here at that secondary carbon. Okay. If we tried to do this same reaction using a carbocation, we would see it move around. So in this case here, this is just a dehydration using sodium bromide and acid to give us our protonated alcohol, which then acts as a leaving group and giving us our carbocation. But what happens whenever we form a carbocation? It's a secondary carbocation. If it can do a hydride or methyl shift to give us a tertiary carbocation, it will. In fact, it does. And therefore, our primary product is the one with the bromine on that tertiary carbon and a rearrangement of our skeletal structure. Okay. This is kind of important because that means if we know we want that secondary bromide, then we know we must go through this other radical reaction. And if we want it to rearrange, then we need to go through a different reaction. So this gives us reaction selectivity that we didn't have before. And just like when we saw in using peroxides in the hydrohalogenation of alkenes, we get an anti-Markovnikov product from that as well. And that also gives us selectivity with radicals we don't have going through other methods. Okay, so now everything we've talked about right now has just been a hydrogen abstraction to an isolated radical. Okay, there's also ways to do this where we have radicals in conjugation. They're allylic or benzylic radicals, and those happen more readily, those happen faster because they are stabilized. They can stabilize that radical over multiple positions. Okay, so when we look at this bromination, and we'll learn about this next semester when we look at brominating benzene, you cannot brominate benzene either by a radical method or by reacting with HBr or bromine itself. It does not work. We have to use a different catalyst system and a whole other way. Okay. And the reason it doesn't do that is that it would have to destroy the aromaticity. And that is a really big, takes a whole bunch of energy to do that. So we don't do that. Okay. But in the case of having a carbon outside of that ring, like in this case of toluene right here, that means that this hydrogen here can be easily removed, giving us a radical here. And that radical is called our benzylic radical. Okay, and remember from our lecture a couple days ago, it is stabilized because we can have it come here. Let's see, it's here, here, here. It can move around the ring and stabilize that radical. So each of those sites only has about a quarter of a radical character, which means it happens really, really quickly. I mean, it's really, really stable. And because it's really stable, we have high selectivity, which means when we create this radical here, that means we get 100% monobromo uh, bromination when we do this. Okay. Remember, bromine is barely exothermic. It can wait around for the selective reaction when you got 100% yield at just this site. Okay. Remember, chlorination is much more exothermic, and therefore it's not as selective. And so you actually end up with a mixture of products, mono and dichlorination, sometimes trichlorination, because there's no selectivity in the system. Okay. Now, the other thing we saw that was really good to have a radical around is we had, let's see, benzylic radicals and then allylic radicals were greater instability than our tertiary, secondary, and primary, right? Okay, so and the benzylic was more stable because we had 4 places to put it on. The allylic's more stable because we have it to be able to go back and forth between here. Okay, so because of this ability to have it stabilized over 2 different atoms, that makes that carbon-hydrogen bond significantly weaker than those other ones, and that makes it easier to remove, which means that we can get these bromination at the carbon next to a double bond very readily. Okay, that means it doesn't have to add across the double bond. It can actually add 1 over from that double bond, that alpha position, and that's actually a more favored reaction than reacting with the double bonds itself. Okay. However, the alkene double bonds do sometimes react. We can get them to react, and I'll show you that in a minute, but the benzene rings won't react. Okay, so we can get selective halogenation while maintaining our alkene. All right, let's take a little more look at that right here. There is a side reaction associated with this, and this is when we actually can add across that double bond. Fortunately, that first addition across that double bond is reversible and can give us our alkene back, okay? So in the case of this, instead of doing an allylic bromination, where we're gonna brominate 1 carbon over from that alkene, we can actually get it to interact to create this new bromine bond and form that radical. Fortunately, that's the reversible reaction because we'll go back to starting materials. However, if we have that reaction and it does not go back to the original alkene, it can do a radical extraction of a bromine and lead to the dibromo compound. Okay, so that would be an irreversible side product of the system. And so to help us stop that, what we want to do is have a very small concentration of bromine at any one time. And that lets us have the formation of our allylic radical. And this type of abstraction cannot happen. If we have very little of this in the solution, then that means this can go back to our alkene, and then it can go by the preferred process of creating our allylic radical. Let's see. There we go. So to inhibit this right here, we want to keep a low amount of bromine in there. Okay, well, the other cool thing is that we can also control this another way. Is that what really helps in this system is to, number one, have a low bromine concentration, but also to use a non-polar solvent. If you use a non-polar solvent, it can't form the bromonium cation right here intermediate. And so if we're looking at a solvent effect here, not allowing it to form that ionic intermediate, and if it doesn't form that ionic intermediate, we can get to that allylic abstraction followed by that allylic bromination. The other way we can do that is to be more selective, not have any bromine in there at all, but use a different source of bromine radical. Okay, and so in this case here, we have what we call NBS. Write that down. It's N-bromosuccinimide. And in this case here, we never have a significant amount of bromine, okay? It'll eventually decompose and you'll create a little bit in solution, but most of the time you'll have a low enough amount of that. The only way we get bromine in a solution is with a bromine radical reacts with a bromine radical. That's the only source of bromine we have in the solution. The rest of the time, we'll just have the bromine radical created by the decomposition of this nitrogen bromine bond, giving us homolytic cleavage with a nitrogen radical here and the bromine radical here. And eventually, we have abstraction of a hydrogen radical onto the succinimide here, and that goes away. Okay. So because we're taking away that bromine as a source of the addition, we now get much more selective about the allylic bromination instead of having that side product, the dibromo product. Okay. So in this case here, we have our very low concentration of our bromine radical. It does our abstraction, giving us our radical here. And again, we have a very low amount of this that only formed from a bromine radical, and that gives us our allylic bromination selectivity. Okay, so we can do it two ways. Do a really nonpolar solvent, do a very small concentration of bromine, or use NBS. And so the preferred method is to use NBS. The only drawback with NBS is it's not very soluble in nonpolar solvents. Okay. So what we have to do is make sure that we do use the NBS and we slowly add it. It does quickly, react with HBr. So we want to make sure we're abstracting that hydrogen and not producing HBr. Once we do that, it produces bromine at a very low concentration. Once we get that bromine at that very low concentration, if we keep it in that low concentration, we get the preferred allylic addition as opposed to the dibromo byproduct. Okay. And so, and the mechanism for the way it does this is it actually ends up abstracting, it protonating this. And so instead of having a homolytic cleavage, we're having a heterolytic cleavage. Bromine is leaving as the bromine cation. Both electrons in this bond are taken away and rearranged to give us this enol form, and then we end up with our succinimide and our bromine as our other product here. Okay. So by changing it from that radical mechanism to this nucleophilic mechanism, we get to that low concentration of bromine, which then can be formed into two radicals and be used in the reaction. All right, questions on that? So when we're just looking at primary, secondary, and tertiary, you're just going to hit it with bromine, chlorine, fluorine, iodine, and more. When we want to do selective bromination on a benzylic position, it works best with bromine because it's very selective. Chlorine gives you a mixture of products. Allylic bromination, again, it's much more selective because of its higher activation energy, but less enthalpy. And that gives us an ability to create that allylic one, but we do have a side product if you have bromine in large amounts around. So we eliminate that by going to the use of N-bromosuccinimide. All right, we got 5 minutes. All right, so let's look at this reaction we looked at in the addition of alkenes. This is again the anti-Markovnikov addition of HBr to an alkene with the use of peroxides. Now that we know a lot more about radicals and radical abstraction and radical stability, we can go through these 3 steps that happen in all radical reactions and again look into the depths of why it shows us anti-Markovnikovs. Okay, so the step when we have peroxides, peroxide is always our initiator. That oxygen-oxygen bond breaks easily, giving us our 2 equivalents of our oxygen radical. The first thing it does is abstract a hydrogen from the bromine, giving us a bromine radical. Okay, now our bromine radical is free to go around and try to find an alkene to add to. And again, if you have a high amount of that alkene, you can form this right here. In this case here, it's symmetrical so that you're forming a tertiary radical, and we formed our bromine on the one side. So this is symmetrical. So we're just seeing that what our steps are. This radical can then abstract a hydrogen from another equivalent of HBr to give us our hydrogen and bromine added across our double bond. But again, we're using that radical mechanism, so we have to have that last step in the stage, which is termination. So we can do that a couple different ways. We can actually terminate it with a bromide radical, giving us the dibromo compound, which is not necessarily desirable, but if you have a whole bunch of your HBr around, you're going to get this as your primary product. You'll only have a little bit of this happen. The other termination step we have is you can get the carbon radical to condense with a carbon radical. And again, this is kind of sterically hindered, so this is also a minor product, but it does form. And notice both of these form neutral species with no radicals generated. That's why it's the termination step. We generate radicals, we propagate radicals, and then we terminate the radicals. The other way we can do it is actually to have a bromine radical to give us bromine. But then that bromine can be reacted with peroxide or light to break it into two bromine radicals as well. So that would actually be considered a reagent that we can actually use, pump back up into the initiation step. Okay, so that's what it is if it's symmetrical. Okay. Now, in the case of HCl and HI, this does not work very well. And you cannot add HCl across that double bond because the abstraction of that hydrogen is endothermic, meaning you have to push a bunch of energy into it. Therefore, it's very unsuccessful with HCl, okay? And just like in the case that bromination with just pure iodine, that using iodine in this iodine radical there, it's too stable as the iodine radical, so we don't add HI across this either. It's also endothermic. So that means it's weird, it's the bromine, which is in between the two, is the only one that can do this step, because in all cases, all of the abstractions and all the bond breakings and makings turn it into an exothermic reaction. Okay, so here's where we get to find out why it's anti-Markovnikov. Okay, so in the case of an unsymmetrical alkene, when we do HBr plus peroxides, do it via radical mechanism, we end up getting that anti-Markovnikov's addition. And here's why. If we look at the activation energy for the abstraction of our, the addition of our bromine to here, we're going to form one of two things. We can have a radical form at the end here, and a part of the bond can form a new sigma bond with the bromine. Okay. In that case, we would get a primary radical. Okay. In the other case, if we had it where we had one electron goes to this tertiary side and one electron goes to form this new sigma bond with bromine, we get a tertiary radical. So what does that mean? Which of these mechanisms has the lower activation energy? The one that has the lowest activation energy is the one that's going to form the more stable radical. Okay, so if we're forming the more stable radical is the tertiary. So we've actually added the bromine to the less substituted carbon. Okay, and it's all because it's a radical mechanism. It's the radical mechanisms that's doing this for us. Because remember, when we did it, when we were adding HBr across the double bond, the hydrogen went to the least substituted side, so it could form the more stable carbocation. Here, the bromine's coming in first, and we're forming this more stable radical. Okay, so our more stable intermediate is the driving force for this. And because bromine is coming in first, bromine's the one that's going to add to that least substituted side, giving us our more stable intermediate. Okay. And therefore, that's why the addition of HBr with peroxides gives us our anti-Markovnikov's product, because we get to the more stable radical intermediate, because it forms that tertiary radical. If we did it in the ionic way, nucleophilic way, we end up getting the hydrogen on the least substituted side to give us the more stable carbocation. And then the bromine comes in last. Okay, so that's why without peroxides, we get the Markovnikov's product. With peroxides and HBr, we get to the anti-Markovnikov product. And notice that because we have the reaction mechanism here, we can easily add HI and HCl using the ionic mechanism because they're good nucleophiles. We don't have to worry about this homolytic bond breakage and bond addition making the reactions not work very well. So we actually want to use the ionic method for HCl and HBr, HCl and HI, but we can choose which way we go with the HBr. We can do Markovnikov's or anti-Markovnikov's. All right, sorry, I ran a minute over. Any questions that you have? Actually, let me go ahead and stop recording, and you can, if you have to run off to class, go ahead and run off to class. If not, go ahead and stay behind and talk to me.